What if I told you that time travel is already real? That astronauts are technically time travelers? That the future is reachable, but the past might be permanently locked? Movies tell us time travel is about changing history. Physics tells us it's about breaking causality, and the universe really doesn't like that. So today, let's answer one question honestly. What does science actually say about time travel? Time travel is one of the most popular ideas in science fiction, but once you strip away the DeLoreans and magic portals, you're left with something far stranger and far more restrictive. This isn't about fiction. This is about real physics, real experiments, and real limits. What is time really? We experience time as something simple, a steady flow from past to future, but physics says that's an illusion. According to Einstein, time is not universal. It's not constant. It doesn't tick the same for everyone. Time is part of a four-dimensional structure called space-time, where space and time are woven together. And once time becomes flexible, time travel stops being fantasy and starts being math. Einstein's special relativity shows that the faster you move through space, the slower you move through time. This has been tested, it's been measured, it's not controversial. Astronauts on the International Space Station age slightly slower than people on Earth. GPS satellites must account for time dilation, or they drift miles off course. If you could travel close to the speed of light, 1 year for you could equal decades for everyone else. You'd return to Earth having barely aged, while the world had moved on without you. That's real time travel into the future. The catch? Reaching those speeds requires impossible amounts of energy. Speed isn't the only way to bend time. Gravity slows it too. The stronger the gravity, the slower time moves. Near a black hole, time nearly stops. Far away, the universe races ahead. So yes, in theory, someone orbiting a black hole could experience minutes, while centuries pass elsewhere. Again, real physics. Still only one direction though. Why the past is the problem. Traveling forward in time is allowed. Traveling backward is where things fall apart. Why? Because of causality. Causes must come before effects. Break that rule, and logic collapses. This leads us to the most famous problem in time travel. You go back in time. You kill your grandfather. Your parent is never born. You're never born, so you never went back in time. So who killed your grandfather? This isn't just a story problem. It's a logical contradiction. And physics does not tolerate contradictions. Any real theory of time travel must solve this. What are possible solutions to paradoxes? Solution 1, the timeline can't be changed. Known as the Novikov's self-consistency principle. If time travel is possible, then only actions that already fit history can happen. You can't change the past, because you already didn't. The universe simply blocks paradoxes. Solution 2, multiple timelines. In this idea, changing the past creates a new universe. You kill your grandfather, but only in a different timeline. Your original history remains untouched. No paradox, just infinite realities. There's no proof this is real, but it avoids logical collapse. Wormholes and time machines. Physics allows something called wormholes, shortcuts through spacetime. If one end experiences time differently than the other, a wormhole could theoretically connect two different moments. Sounds promising, but there's a problem. Wormholes may require negative energy, collapse instantly, or destroy themselves through quantum instability. They're mathematically allowed, but physically unproven. There's one final obstacle to backward time travel: entropy. Entropy always increases. Eggs break, but don't unbreak. Heat spreads, but doesn't reconcentrate. Memories form, but don't reverse. This creates the arrow of time. To travel backward, the entire universe would need to reverse entropy. There's no known mechanism for that. Does the universe prevent time travel? Stephen Hawking proposed the chronology protection conjecture. The idea is simple. The laws of physics actively prevent time travel to the past to protect causality. Any attempt to build a time machine would destroy itself before working. Reality enforces consistency. So here's the honest answer. Time travel into the future is real and unavoidable. Time travel into the past may be impossible. Not because we lack imagination, but because the universe seems structured to forbid contradiction. Time bends, time stretches, time slows, but it does not rewind. And maybe that's the point. The universe is nearly 14 billion years old. It contains trillions of galaxies. It's with billions of stars, and many of those stars have planets. So here's the question that keeps scientists up at night. If intelligent alien life should be common, why is the universe completely silent? No signals, no ships, no megastructures. So where is everybody? This question is known as the Fermi paradox. It's not about whether aliens could exist. It's about why, given everything we know, they should exist. And yet we see nothing. Why science expects aliens? Let's start with the math. Our galaxy alone contains hundreds of billions of stars. Many of those stars have planets. Many of those planets are Earth-sized. Some sit in the habitable zone, where liquid water can exist. This led to the Drake equation, which estimates how many technological civilizations might exist in the Milky Way. Even pessimistic versions of the equation suggest intelligent life should arise multiple times. Some civilizations should be millions of years older than us. And that's important, because a civilization only a few million years more advanced than humanity could theoretically colonize the entire galaxy, leave unmistakable evidence of its existence. Yet when we look out into space, nothing. What we've actually looked for. We're not just waiting for aliens to show up. Scientists have searched for radio signals, laser emissions, artificial light on distant planets, Dyson spheres, massive structures built around stars, industrial pollution in alien atmospheres. So far, silence. No clear, undeniable evidence of intelligent extraterrestrial life. This is the paradox. One solution is unsettlingly simple. Maybe we're rare. The rare Earth hypothesis suggests that complex life requires an absurd number of lucky breaks. A stable star, a protective magnetic field, plate tectonics, a large moon, the right chemistry, the right timing. Miss one of these, and intelligent life never appears. Under this idea, microbial life may be common. Intelligent civilizations may be extremely rare. We might be one of the few, or the only. Now for the darkest explanation. The Great Filter. The Great Filter is a step in evolution that is incredibly hard to survive. Possible filters include life forming at all, complex cells evolving, intelligence emerging, technology developing, avoiding self-destruction. Here's the terrifying part. If the filter is behind us, we're incredibly lucky. If the filter is ahead of us, then most civilizations destroy themselves before spreading into the stars, and the silence of the universe becomes a warning. Another possibility? Aliens exist, but we're missing them? The zoo hypothesis. Advanced civilizations may deliberately avoid contacting us. Earth could be a nature preserve, or a simulation, or something being observed quietly. Technological mismatch. They don't use radio. They communicate in ways we can't detect. They've moved beyond physical forms entirely. We may be listening with Stone Age tools. Time may be the issue. Civilizations might be common but short-lived. The universe is billions of years old. Human civilization has existed for only a few thousand. Two civilizations could arise in the same galaxy and miss each other by millions of years. The galaxy might be full of ruins. Maybe advanced civilizations go quiet. We assume advanced civilizations expand outward. But what if that's wrong? What if advanced intelligence turns inward, lives in virtual realities, minimizes energy use, avoids large-scale engineering? The loud, galaxy-spanning empires of sci-fi might be inefficient or extinct. Silence might be the end state of intelligence. One final possibility. There is no paradox at all. Our assumptions may be flawed. Intelligence may not be common. Expansion may not be inevitable. Detectability may be rare. The universe might be quiet, because quiet is normal. The Fermi paradox isn't really about aliens, it's about us. It asks, how fragile is intelligence? How long do civilizations last? Is survival the exception or the rule? The universe's silence could mean we are incredibly lucky, or we are incredibly early, or we are in danger. And until we find even one other voice out there, the question remains, where is everybody? Look around you, the space between atoms, the space between planets, the vast emptiness between galaxies. We call this nothing. But according to modern physics, that nothing should contain so much energy that the universe should have torn itself apart the instant it was born. Galaxies shouldn't exist, stars shouldn't exist, you shouldn't exist. And yet, here we are. This problem has a name: the vacuum catastrophe, and it is one of the worst predictions ever made by physics. The vacuum catastrophe isn't a fringe theory. It's not speculative science. It comes directly from our two most successful frameworks, quantum field theory and general relativity. Both work incredibly well, but when they describe empty space, they disagree by a factor of 10 to the power of 120. That's not a rounding error. That's a crisis. First, let's go over what is a vacuum. In everyday language, a vacuum means nothing. No air, no matter, no energy. Classical physics agreed, but quantum physics shattered that idea. In quantum field theory, the universe is filled with fields: electron fields, quark fields, photon fields, the Higgs field. Particles are just excitations in those fields, and even when there are no particles, the fields remain. This lowest possible state is called the quantum vacuum, and crucially, it is not empty. According to the Heisenberg uncertainty principle, a system can never have perfectly defined energy. That means quantum fields can never fully stop fluctuating. Even in their lowest state, they vibrate. This leftover motion is called zero-point energy. Think of it like this. In classical physics, a pendulum stops at the bottom. In quantum physics, it never truly comes to rest. So empty space contains energy. It's measurable. One of the clearest demonstrations is the Casimir effect. Place two metal plates extremely close together in a vacuum. Quantum fluctuations between them are restricted. Outside them, they're not. This imbalance creates a tiny force pulling the plates together. That force has been measured. Matches quantum predictions. Comes purely from vacuum energy. So the vacuum isn't nothing. It's a seething background of energy. Here's where things go wrong. 1/2 times Planck's constant times frequency. There are infinitely many modes, at all wavelengths, at all energies. Add them all up and you get infinite energy. Physicists introduce a cutoff. Quantum field theory probably breaks down at very high energies. The most reasonable cutoff is the Planck scale. Even with that conservative assumption, the predicted vacuum energy density is 10 to the power of 120 times larger than what we observe. This is the vacuum catastrophe. So why does this energy matter? In most areas of physics, absolute energy doesn't matter. Only differences do, but gravity is different, according to Einstein. Energy tells space-time how to curve. Vacuum energy gravitates. It acts like a cosmological constant, causing space itself to expand. If quantum theory were right about vacuum energy, space would expand insanely fast. Matter would never clump. Galaxies would never form. The universe would be empty forever. What we actually observed. Observations show the universe is expanding. The expansion is accelerating. Something called dark energy is responsible. Dark energy behaves exactly like vacuum energy, but its measured value is tiny, almost zero. Quantum theory screams enormous, while cosmology whispers barely anything. Both theories are correct everywhere else. Here they violently disagree. Why this isn't just a math error? You might ask, why not just subtract the vacuum energy? In non-gravitational physics you can. In gravity you cannot. Gravity responds to absolute energy. Subtracting it by hand isn't a solution. It's an admission we don't understand something fundamental. One proposed solution is supersymmetry. Every particle has a partner. Bosons cancel fermions. Positive energy cancels negative energy. In a perfectly supersymmetric universe, vacuum energy equals zero, but supersymmetry is broken. We haven't seen superpartners. Even if SUSY exists, it only reduces the problem slightly, not by 120 orders of magnitude. The Higgs field makes it worse. The Higgs field has its own vacuum energy. Its contribution alone should curve space-time violently, destroy the universe, yet it doesn't. So now we don't have one mystery. We have many cancellations happening simultaneously. Perfectly. Why? No one knows. To match observations. Enormous contributions must cancel almost exactly, leaving a tiny leftover. This is called fine-tuning. Physicists hate fine-tuning. It usually means a missing symmetry, a hidden mechanism, or a deeper theory waiting to be found. One controversial explanation is the anthropic principle, the idea. Many universes exist, each has a different vacuum energy. Most are lifeless. We observe this one because it allows observers. In most universes, expansion is too fast. Matter never clumps. Life never forms. This explanation feels unsatisfying, but it works. String theory predicts a vast landscape of possible vacua, each with different physical constants, possibly 10 to the power of 500 universes. Vacuum energy varies across this landscape. We may live in a rare, habitable pocket. Critics say this isn't testable. Supporters say it may be unavoidable. Some propose vacuum energy evolves over time. Gravity doesn't respond to vacuum energy normally. Our understanding of space-time is incomplete. All are speculative. None are confirmed. The vacuum catastrophe isn't a detail. It's a foundational crack. Empty space should weigh more than everything in the universe combined. Yet it doesn't. That means something is canceling it, or something is missing. Or reality is structured in a way we don't yet understand. The universe appears calm, but mathematically, it shouldn't exist at all. Right now you exist in one universe, but what if that's not the whole story? What if this universe, everything we can see, measure, and experience is only a single region of a much larger reality? A reality where other universes exist. The laws of physics can change. Every possible outcome may actually occur. It's called the multiverse. And it emerges naturally from some of our best theories of physics. The multiverse isn't one theory. It's a family of ideas, all suggesting that what we call the universe might not be everything. Physicists didn't invent the multiverse because it sounds cool. They were forced into it by problems they couldn't otherwise solve. Problems like why the laws of physics seem perfectly tuned for life, why quantum mechanics allows multiple outcomes, why the early universe expanded the way it did. Each of these independently points toward more than one universe. Why physicists even consider a multiverse? Let's start with something unsettling. The universe appears finely tuned. Small changes to fundamental constants would destroy it, if gravity were slightly stronger. Stars burn too fast, slightly weaker. Galaxies never form. Change the cosmological constant. Space expands too quickly for matter to clump. Change particle masses. Chemistry fails. These aren't minor changes, they're catastrophic. So the question is simple. Why do the laws of physics have exactly these values? The fine-tuning problem. There are only 3 logical explanations for fine-tuning. 1. Necessity. The constants couldn't be different. 2. Design. They were intentionally chosen. 3. Chance. They vary across many universes. Physics strongly prefers explanations that don't invoke intention. That leaves chance. But chance only works if there are many trials, which means many universes. This idea is formalized as the anthropic principle. It says, we should not be surprised to observe conditions compatible with our existence. If millions of universes exist, most are lifeless. A few allow complexity. Observers necessarily arise in those few. So the universe looks fine-tuned not because it was designed, but because only fine-tuned universes can be observed. This reasoning is uncomfortable, but it's logically consistent. Level 1 multiverse. Beyond the cosmic horizon. The simplest multiverse is also the least controversial. It says, space may be infinite. We can only see a finite region because light travels at a finite speed. Beyond our cosmic horizon, space continues. Matter rearranges itself in different ways. If space is infinite, every possible configuration of matter occurs somewhere, including regions identical to Earth, including copies of you. Same laws, same constants, different initial conditions. This isn't speculation. It's a direct consequence of infinite space. Level 2, multiverse. Inflationary bubbles. Now we go deeper. Inflation. Inflation theory explains why the universe is flat, uniform, structurally smooth. It proposes that the early universe expanded exponentially fast. Inflation works extremely well, but many models predict something else. Eternal inflation. Inflation may never fully stop. Instead, it ends locally, creating bubble universes, while continuing elsewhere forever. Each bubble is a universe. And here's the key. Each bubble may have different physical constants. Why this solves fine-tuning? In a bubble multiverse, laws of physics vary. Most universes are lifeless, some are stable, We live in one of the rare bubbles where stars form, chemistry works, life is possible, fine-tuning becomes selection, not mystery. Level 3 multiverse. Many worlds of quantum mechanics. Quantum mechanics introduces another multiverse. The measurement problem. Quantum systems exist in superpositions. But when measured, we see one outcome. Why? The many worlds interpretation. Many worlds says the wave function never collapses. Instead, every outcome happens. The universe branches. Each branch contains a different result. Every quantum decision creates parallel histories. No randomness, no collapse. Just branching reality. Are these really other universes? Some argue these branches are mathematical, not physically real. Others argue they never interact, have separate histories, and are effectively separate universes. Either way, the mathematics work. That's why physicists take this seriously. Level 4 multiverse. Mathematical reality. This is the most radical version. It proposes every mathematically consistent structure exists physically. In this view, reality is mathematics. Physics doesn't describe reality, it is reality. Every possible universe defined by math exists. Our universe is just one structure among infinitely many. This idea is deeply controversial, but it addresses a haunting question. Why does mathematics describe the universe so well? String theory and the landscape. String theory strengthens the multiverse case. It predicts extra dimensions, many ways to compact them, each yielding different physics. This creates the string landscape, possibly 10 to the power of 500 different vacuum states, each corresponding to a different universe. Vacuum energy varies across this landscape. This ties directly into dark energy, the vacuum catastrophe, and fine-tuning. Can the multiverse be tested? This is the biggest criticism. If other universes are unobservable, is the multiverse scientific? Possible tests include statistical predictions, constraints on constants, imprints from bubble collisions. So far, no direct evidence, no definitive falsification. This keeps the debate alive. Science or philosophy? Some physicists say the multiverse is unavoidable. Rejecting it requires rejecting successful theories. Others say it undermines scientific explanation. It replaces prediction with selection. Both sides include Nobel laureates. This isn't fringe. It's an open debate at the foundation of physics. The multiverse may sound outrageous, but it emerges naturally when we take mathematics seriously, push theories to their limits, refuse to stop where intuition feels comfortable. Reality may be far larger than a single universe, and if that's true, then the universe we call home is not the whole story, just the one where we happen to wake up. Imagine you take two particles, you connect them in a way that physics allows, then you separate them across a room, across the planet, across the universe. Now imagine this. You measure one of them, and instantly the other one responds, no signal, no delay, no matter how far apart they are. Albert Einstein hated this idea so much that he called it spooky action at a distance, and yet it's real, it's measurable. And it may be more fundamental to reality than space and time themselves. This phenomenon is called quantum entanglement. Before we talk about quantum entanglement, we need to talk about how the world should work according to common sense. In everyday life, objects have properties. Those properties exist whether or not we observe them, and objects are fundamentally separate. If I flip two coins, each coin lands independently. Knowing the result of one tells me nothing about the other. Even if two objects interact and then separate, we assume something crucial. Once separated, each object carries its own information. This assumption is called local realism. Local. Nothing influences anything else faster than light. Realism. Properties exist before we measure them. Classical physics is built on this idea, and for centuries it worked perfectly. Then quantum mechanics arrived. Quantum mechanics forced physicists to accept something deeply uncomfortable. At the smallest scales, particles don't have definite properties. They exist in superpositions, multiple possibilities at once. An electron isn't just here or there. It's described by a wave function, a mathematical object that encodes probabilities, not facts. Before measurement, a particle doesn't have one position. It has a range of possible positions. Measurement doesn't just reveal reality, it seems to create it. Already this is strange, but it gets worse. Because when you bring multiple particles into the picture, quantum mechanics allows something even more radical. In classical physics, two objects equals two separate descriptions. In quantum mechanics, two objects can share one wave function. This is where entanglement begins. An entangled system is one where you cannot describe particle A independently. You cannot describe particle B independently. Only the pair together has a complete description. They stop being two things. They become one system even when separated. Let's talk about spin. Spin is a quantum property, not literal rotation, but it behaves like angular momentum. An electron's spin can be measured as up or down. Now imagine a particle decays into two electrons. Physics requires total spin must be conserved, so the system enters this state. Neither electron has a definite spin, but the pair must always be opposite. Before measurement, electron A is not up or down, electron B is not up or down. They exist in a shared superposition. Now you measure electron A, you get up. Instantly, without delay, electron B becomes down, even if it's light years away. Why this shouldn't be possible? At this point, classical intuition screams, they must have known ahead of time. That's what Einstein thought. He believed each particle carried hidden variables instructions set at creation. Quantum mechanics, he argued, must be incomplete. This idea became famous as the EPR paradox. Einstein wasn't claiming quantum mechanics was wrong. He was claiming it was missing something. In 1964, physicist John Bell did something extraordinary. He proved that if hidden variables exist and reality is local, then certain statistical limits must hold. These limits are called Bell inequalities. Quantum mechanics predicts they will be violated. So physicists tested it again and again and again over decades, with increasing precision. The result? Bell inequalities are violated every time, meaning local hidden variables do not exist. Nature is not locally realistic. Something has to give either. Information travels faster than light, or particles don't have independent properties. Quantum mechanics chooses the second option. Let's be a little more clear. Entanglement is not faster than light communication. Telepathy, consciousness creating reality. Particles sending messages. You cannot control the outcome. You only discover correlations after comparing results using classical communication. Relativity is safe. Causality remains intact. What's broken is our assumption that distant objects are independent. Modern physics treats entanglement as a resource, like energy, like matter, like information. This allows quantum teleportation as in state transfer, not sci-fi transport. Quantum encryption, quantum computing. Without entanglement, quantum computers lose their power. It is the engine. Why we don't see this every day? If entanglement is so fundamental, why does the world look classical? The answer is decoherence. Quantum systems constantly interact with air, light, heat, noise. They become entangled with the environment. This spreads quantum information so widely that it becomes unobservable. Entanglement doesn't disappear. It becomes inaccessible. What does this mean for reality? Entanglement forces a terrifying conclusion. The universe is not built from independent parts. Reality is relational. Wholes exist before parts. And space itself may emerge from entanglement. Some modern theories suggest. Geometry arises from quantum correlations. Space-time is stitched together by entanglement. Wormholes and entanglement may be two sides of the same coin. This is not science fiction. This is active theoretical physics. Quantum entanglement tells us something profound. Separation may be an illusion. The universe may be deeply interconnected in ways space and time cannot fully describe. Einstein hated this idea. But experiments don't care about comfort. They care about truth. And the truth is stranger than we ever imagined. If you enjoyed this chat, consider subscribing, because the universe is far weirder than it looks. I will chat with all of you in the next one. Bye for now.